As you can see that if you have a local descriptor, you can explain the reactivity from point to point in a molecule. Okay, suppose if you have a molecule with electron density like this, what is the reactivity here, what is the reactivity here? Also you can talk about the reactivity of the whole molecule when it sees another molecule. So one is global, another is local. Now obviously you can think about this, that if you know the local descriptor and you integrate over the whole molecular space, you must get back the global descriptor. Okay, that means so if I call hardness, we have shown actually this is 1 by n double integral eta r prime fr prime rho r dr prime, let us say. Okay. So what you can see, this one tells you, of course, at 2 points r and r prime, if you want to focus your attention, and then you calculate this quantity, then you integrate over the whole space, whole molecular space. Similarly, and this eta r prime, as I told you, half del 2 f rho r del rho r prime. That means is the second order functional derivative of the Hohenberg-Kohn-Sum universal functional. So if you know the Hohenberg-Kohn-Sum universal functional, where you have the kinetic energy, you have the electron-electron repulsion, you have exchange correlation potential, you can calculate this eta. And the way it is written, as we have learned from DFT, that any property can be written as a density functional. So the reactivity descriptors also in principle, so this is a density functional. We can write it in the form of a density functional. Suppose if I call S, this is integral S of R dr. If we call omega, that is integral omega of R dr. So this felicity, local softness. So as you can see that point to point measure, if you integrate over the whole molecular space, I must get the corresponding global descriptor. So this is how we get hardness, how we get. So it is not simple eta as integral of, so eta as integral of eta r dr, this cannot be obtained. So this you have to go for this particular route. So this you cannot do it because this is ambiguous, local hardness is ambiguous, but you can do it, let us say, for softness, you can do it for electrophilicity. Okay. And this SR and WR, then S into f of r, omega is omega into this omega r is omega into f of r. Okay. Now, when you do the calculation, let us say you remember f plus, f minus, etc. That means you have to add electron or you have to take out an electron. So the total procedure would require either a kind of delta SCF procedure, or if you apply Koopman's approximation in terms of the frontier orbitals. Okay, frontier orbital densities. So like if I call F plus R, I can write it as del rho r del n Vr plus. That means what? This is rho n plus 1 r minus rho n r. You see, this is my delta SCF. And what is this? Rho n plus 1 minus rho n? What is that? If you have n plus 1 number of electrons, what is the total density? Minus n number of electrons, what is the total density? So where is that extra electron density? It's in LUMO, isn't it? So this is according to Koopman's theorem, approximately this is my, so this is for your nucleophilic attack, rho LUMO. And that is quite obvious. How much is there LUMO, the extra electron density in nucleophile will attack there? If it is more prone towards nucleophilic attack. So that is the measure, your F plus R. Okay. Similarly, your F minus R would be del rho R del n Vr minus, and this would be your rho n R minus rho n minus 1 R, and accordingly this would be your rho HOMO. And your F0 R is half of F plus R plus F minus R, that is your half of, if you add these two, it should be your rho n plus 1 minus rho n minus 1, so this is half rho LUMO plus rho HOMO. Okay. So this is for your radical attack. So how to calculate Fukui function now? I am doing this just how to calculate it. You find out the density profile for the anion and neutral molecule, subtract point to point you subtract. You get the LUMO density in Koopman's theorem. So if you want to do only the LUMO density, that will give roughly this value, and this is nothing but your F plus R. So that map, Fukui function map, will tell you these are the locations where nucleophilic attack is preferable. If you do the second one, it will tell you the locations of in the molecule where electrophilic attack is favorable. Okay. And similarly where the radical attacks are favorable. Now as I told you, and you know any one of these Fukui function, if you integrate, it must give you 1. Okay, because it's a del rho del n, and this integral means integral rho at dr is n, del n is 1. So it must give you 1. So the Fukui function is normalized to unity. Now let us say if we define atoms in a molecule, there are various ways depending on population analysis schemes. You can have Mulliken population analysis scheme, you can have Loveday population analysis scheme, you can have Hirschfeld population analysis scheme, and so on. So that will tell you how you define a molecule and the atoms inside a molecule. So if you have a molecule like this, and let us say I define, or Bader's one, let us say these are different atoms in a molecule. If you know the electron density, I can now define various regions. They are called basins. So in a molecule, if you have A atom, B atom, C, D, E, F, so this is atomic basin of A in the molecule A, B, C, D, E, F. Okay. Now, if I do this, instead of integrating the whole, if I integrate, let us say only over this basin, okay, that means this is, let us say, my Fukui function map. I am integrating over only this basin. So that I will call condensed to atom variants of Fukui function on atom A. Do you understand? So now I am talking about, let us say if I talk about now electrophilic attack, nucleophilic attack, not any point in a molecule, rather I will tell that to this atom in a molecule. Okay. So I am taking more of a chemist language, but there is some arbitrariness in the definition of an atom in a molecule itself. Okay. As I told you, these are population analysis schemes, atoms in a molecule. So, if I define this, so we will call condensed to atom variants. So, if I call this as F k alpha, now there is no R dependence. I have integrated over, let us say, kth atom. So, this would be integral of, let us say, rho n plus 1 on that kth atom. So, this one is what we call q k n plus 1 minus q k n, where q k is electron population. So, this is the density over the kth atom. So, if you integrate, how many electrons are there? That is called electron population, and that is why you get, depending on population analysis scheme, we will call it Mulliken population or Loveday population or Bader population. Okay. So, if you want to enter into any local description of reactivity, you have to know the population analysis schemes. Okay. Electron population of atom K. Okay. Or I can call on atom K, let us say. Okay. So, similarly, I have written Fk alpha. Alpha may be your sorry. This is Fk plus. Similarly, my Fk minus would be Qkn minus Qk n minus 1, or similarly I can call it as a Q LUMO, this one as Q HOMO, and this one would be half of let us say Qkn minus 1 minus Qkn, or it would be half of, let us say, Q LUMO plus Q HOMO. Okay. But this is on kth atom, remember, that is very important. It is on the kth atom. What is the contribution there? So, if you do this, so you can get a condensed to atom local softness also. Sk alpha is, say, your S into Fk alpha, and omega k alpha is omega into Fk alpha. That means you have condensed to atom say Fouquet function for nucleophilic, electrophilic or radical attack on kth atom multiplied by the global electrophilicity will give you the local electrophilicity for that kth atom and for that type of attack. Okay. Now, sometimes in chemistry what we do, we say that this functional group behaves like a very good electrophile. So, you have to know now group philicity, not on atom, one atom. So, we call it group philicity. Say if I call omega m k alpha, this is sum over k equal to 1 to m omega m k alpha. That means, or I am writing it like this. omega k alpha, k equal to 1 to m. Like suppose if you talk about NH2 radical, omega n alpha plus 2 times omega H alpha, that will give you the corresponding omega alpha for the NH2 radical. Okay. So, this is like functional groups Puppy function, electrophilic behavior or nucleophilic behavior or radical attack behavior, that can be obtained through group philicity. Okay. Now, you can define a specific group, whether it would behave like electrophile or nucleophile. If you have two such groups interacting, which one will be a better electrophile, which one would be a better nucleophile, that also can be obtained through the comparison of these values. Okay. So, we have understood global reactivity descriptors, local reactivity descriptors, also the condensed atom variants of various local reactivity descriptors, including this various population schemes, and also the condensed to atom variants, and also we have seen the group philicity sort of stuff, or you can do group softness also exactly in the same fashion. Okay. Now, we generally appreciate these global reactivity descriptors in terms of several electronic structure principles. Okay. So, we will see conceptual DFT based conceptual DFT based electronic structure principles. So, that means suppose we know various global and local descriptors of their condensed atom variants. What extra information on their reactivity, stability, bonding, structure, even in dynamics also, we can obtain out of those reactivity principles. Can you connect them to, let us say, thermodynamics, kinetics, and so on. So, how much time do I have? 47. So, I can finish this. So, first I will tell you electronegativity equalization principle. What is that? Suppose several atoms are forming a molecule. When they will come very close to each other, there will be electron flow from the atom with lower electronegativity to the atom with the higher electronegativity. And as the electron flow will continue, and electron flow means you can explain in terms of acid-base reaction, Lewis acid-Lewis base, or you can explain in terms of a redox reaction, depending on what type of reaction you are talking about. in terms of electron flow. Gradually what happens, the electronegativity of higher electronegative atom will go down, and lower electronegative, because it is getting electron, so say it is losing electron rather, so it will go up. Ultimately what will happen, at the equilibrium when there is no more electron flow, the electronegativity of all the atoms in a molecule will get equalized. They will have same electronegativity, which we will call molecular electronegativity. We can write in the electronegativity what we have learned just now, that also like Mulliken type electronegativity I plus A by 2, that will give me this principle. Okay. And the molecular electronegativity, actually chi molecular would be product over J chi J equal to 1 to alpha to the power 1 by alpha. That means this is what we call geometric mean, isn't it? Alpha th root of chi 1 into chi 2 into chi alpha, where you have alpha atoms. So when the electronegativities are equalized, the molecular electronegativity will be same, and that can be obtained as the isolated atom electronegativities of the atoms and their geometric mean. So you get another principle, associated principle. This is geometric mean principle of electronegativity. Okay. Now for hardness also, you get hardness equalization principle. And accordingly, you get geometric mean principle of eta. Okay. Then you get electrophilicity equalization principle. And geometric mean principle of omega. And of course you get another one, arithmetic mean principle. Arithmetic mean principle means here you have to take product and then the square, to say alpha th root. Here you have to add all of them divided by number. That is what we call arithmetic mean. Arithmetic mean principle of softness. Softness obeys arithmetic means principle. What? Which one? Geometric mean principle of hardness. So this is geometric mean principle of hardness, electrophilicity equalization principle, geometric mean principle of electrophilicity, arithmetic mean principle of softness. Okay. And as I explained in case of electronegativity, you can explain other quantities also exactly in the same fashion. Sorry. 1, 2, 3, 4, 5, 6, 7. There are 7 here. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. 8. So, you will hear this is called hard soft acid base principle or HSAB principle. What it says that if you have some hard acid for both thermodynamic conditions, thermodynamic reasons and kinetic reasons, it would prefer to react with a hard base rather than a soft base. And again a soft acid would prefer to react with a soft base. So, hard prefers hard, soft prefers soft for both thermodynamic and kinetic reasons. That is basically HSAB principle given by Ralph Pearson. Okay, this is Pearson's hard soft acid base principle. And this whole of conceptual DFT, so this is called Ralph Pearson, it started with Robert G. Parr. Okay, it started with, have you ever heard his name? He was my postdoc guy, Robert G. Parr. Okay. Actually, none of them is alive now. Then I will talk about a principle which myself and Robert Parr we developed. So, this was qualitatively it was told in the context of hard soft acid base principle by Pearson, but we had proven this given the proof of maximum hardness principle. Also we have given proof of hard soft acid base principle also. So, what is maximum hardness principle? It says that for a stable system that hardness would prefer to be maximum. That means suppose you have several geometries, the geometry which is most stable will also be associated with the maximum value of the hardness. Okay. Not only for an isolated molecule, when there is a chemical reaction, it tells that the spontaneous chemical reaction, the direction of the spontaneous chemical reaction is the direction in which the hardness is getting maximized. So, not only it can talk about the isolated molecules, stability of isolated molecules, in fact, it can explain aromaticity also. Maybe Friday I have a lecture where I will tell you on that. You can understand the feasibility or spontaneity of a chemical reaction. The direction, if you calculate what was the hardness before the reaction, what is the hardness after the reaction, if the hardness increases, that is the spontaneous direction and the actual chemical reaction will take place in this path. Okay. Then we had shown, this was shown by us, minimum polarizability principle. Polarizability principle. Also we had shown minimum magnetizability principle. And also minimum electrophilicity principle. That means they are all self-explanatory. If you take two molecules or two different structures of the molecules, which one is having lower electrophilicity, that one would be more stable. And the reaction in which electrophilicity is decreasing, like in thermodynamics, for a constant temperature pressure reaction, the direction in which the Gibbs free energy is decreasing, that is the spontaneous direction. Here also you can write it in terms of like hardness is increasing, electrophilicity is decreasing, magnetizability decreasing, polarizability decreasing. Okay. So I thought that I will tell you spin dependent part also, but I think it is not possible. Tomorrow I will tell spin dependent part also. Okay. Stop. Say global reactivity descriptors we have shown mu, chi, eta, s, omega. So these are global reactivity descriptors, and local reactivity descriptors, say first one of course your density, then you have the Fukui function, then you have local softness, you have the philicity, you have chi r prime, you have the hardness kernel, and so on. And similarly you can have their condensed to atom variants and also condensed to a functional group. Okay, the group philicity or group softness, that also we discussed. So now today what will you do? Spin dependent generalizations. So all those descriptors we will see, say if you can separate out, because if you want to see the dependence of spin, so far we neglected that particular variable. So how will you go for it? Now suppose now instead of orbitals we are thinking about spin orbitals. Okay. And here let us say you have for alpha spin, you have for beta spin. So like here you have some, and here let us say down spin you have some. Okay. Now depending on if they are same, it will be basically spinless, plus up, minus up. So it would be like say total spin is 0, that means a singlet type situation. But if let us say alpha spins are more, then you will get like doublet, triplet, quartet, etc. Now suppose we want to describe the reactivity separately for alpha spin and the beta spin. Let us say the density associated with this I will call it rho alpha, and density associated with this I will call rho beta. Okay. Then obviously you can see your rho alpha plus rho beta is your rho, like rho of r. This is what we call electron density. Now suppose, now if I want to do this is the extra spin density. This one we call spin density. There are many people do calculation, they give spin density maps, and majority of them they don't know what is spin density. This is actual spin density. Okay. Just rho alpha minus rho beta. If I integrate this quantity, that means n alpha plus n beta will give me n. This is integral of rho dr. And n alpha minus n beta I will call ns. So this is what we call, say, electron number, and this is called spin number. Okay. So you can see electron density and spin density, electron number and spin number. Spin number will tell you the extra unpaired spin, how many you have in your system. Okay. Now we will consider case by case. Say mu n is del E del n at constant ns and Vr, whereas mu s is del E del ns at n Vr. So this one is the old stuff what we have learned. This is called chemical potential, and this is called spin potential. Okay. So we get mu n and mu s, they are chemical potential and the spin potential. Okay. Now, if you go to the second derivative, there is a hardness. You can have eta n n, that is del mu n del n at fixed ns and Vr. Okay. Then eta s s is del mu s del n s n Vr. Okay. So you can see you can have 4 different types of hardness. You have eta n s is del mu n del n s at fixed n and Vr. And because of the symmetry, this would be same as del mu s del n ns Vr. This one will call eta s n. Okay. So you can see 4 different types of hardness variables. Now say 2 different types of chemical potential, 4 different types of hardness. Now here you remember, and obviously wherever I have obtained let us say chemical potential and spin potential, you get the corresponding electronegativity also, just with a negative sign. Now in this case, now we will go for let us say electrophilicity, and reciprocal of all these will give you the corresponding softness. Okay. Omega is mu square by 2 eta. So now you take mu n set will give you one type of omega, mu s set will give you one type of eta, and eta you have to choose considering which are remaining constant. Okay. That means when you define mu n, your ns and Vr is del E del n at constant ns and constant Vr. So constant ns, constant Vr means this one and this one. So you can take these two, and 2 different types of omega you will get. Similarly, if you start with mu s, their n and Vr, they were constant, there this one and this one you can take to define the electrophilicity. So do you understand? So 4 different types of electrophilicity you can get. Okay. That depends on your system. Okay. That will depend on whether, let us say, you are doing a chemical reaction where only alpha spin is preserved, beta spin is changing, or whether only number of electrons are changing, there is no change in spin number. But there are several reactions, although we know a general principle that the chemical reactions generally follow when your spin multiplicity does not change. But there are certain reactions where spin multiplicity do change during the reaction. In that case, you have to check whether both N and Ns they are changing, whether only Ns is changing, N is remaining same. So number of electrons are not changing between reactant and product, but Ns is changing. Okay, like there are spin flipping reaction. In excited state, you have singlet to triplet transfer. Then you have to take, depending on which type of reaction you are studying, judiciously you have to choose those descriptors. Okay. So these are the conditions, like here N V are constant, Ns V are constant, like this. So which one is remaining constant during that process? You take that one. Okay. Now we will go to the local descriptors. Local descriptors like rho already we have discussed. You have electron density, you have spin density. Now let us say Fukui function. F n n r. This is del rho del n at Ns Vr this is del mu s nn, del mu n del Vr n ns. Okay. Suppose if I do f ns r, this would be del rho del ns at n Vr is same as del mu s del Vr n ns. Okay, you write down another two, f ss and f sn. Do you understand? So, because Fukui function can be written in two different ways that we have seen. So, f ss and f sn. Now, you can see the local softness and philicity. I must tell you, if I take like Fukui function or density, they are normalized, like rho r is normalized to n, Fukui function is normalized to 1. So, that means within a molecule, if I see, I sum over all the reactivities of all the centers, that must be conserved. Okay, this is the reactivity conservation. Now, in this case, what happens? It is within the molecule. It can tell you the reactivity of one point with respect to the reactivity of the other point in the same molecule. That means, in general, like rho r, Fr, these are all intramolecular local reactivity descriptor, intramolecular, within the molecule. But suppose if I talk about S of r, omega of r, there you have some global into local. These are one global quantity multiplied by a local quantity. And the global quantity will change from molecule to molecule. So, you can compare now suppose you have say similar type of molecules, let us say carbon monoxide, carbon dioxide or nitric oxide, nitrous oxide, nitrogen trioxide, all of them the reactivity if you want to compare say NO with N2O with let us say N2O3, N2O5 and so on, NO2. You cannot use these. So, within one molecule you can tell reactivity of nitrogen and reactivity of oxygen, how do they compare? But if you want to compare reactivity of nitrogen with the reactivity of nitrogen in another molecule, you have to go for this. They are called intermolecular local reactivity descriptors. Okay. So, this is, even if we do not go to the spin polarized case, we can still, when we do not talk about spin, there also you have to remember that when you compare two molecules reactivity, you have to go for, always you have to go for intermolecular descriptors. So, FR is not adequate if you want to compare the reactivity of a site in one molecule with the reactivity of another site in another molecule, that you cannot do. Within the same molecule you can do. Okay. So, this SR and omega R, again S, you have various possibilities. Omega also you have various possibilities that we have seen. Fukui function also you have various possibilities. So, you have to couple properly, as I told you, just looking into the corresponding constants, so that they should match, and then you can construct the local versions of local softness and philicity. Okay. Now, this whatever I told you, this is called NNS-VR representation. So, this whole representation is called NNS-VR representation, because here everything I am trying to do the variations. Previously I did only N and VR, now I am doing N, NS and VR. Okay. Now, suppose we do not want to bring in something extra, we want to go to just the basic formalism itself. So, there we will do N alpha, N beta, VR representation. This is another representation. We know the meaning of N alpha, N beta, etc. So, here suppose mu alpha is del E del N alpha N beta VR. Mu beta is del E del N beta N alpha VR. Eta alpha alpha is del mu alpha del N alpha N beta VR. F alpha alpha is del rho alpha del N alpha N beta here. You get the other, you write down the other forms of hardness like alpha beta beta, alpha alpha, eta alpha beta, eta beta beta, eta alpha beta and eta beta alpha. Similarly, F beta beta, F alpha beta, F beta alpha. Get the forms. Do you understand? This is much easier. You have to be very careful about the subscripts, nothing else, and the constants. Whatever is not varied, that is constant. Okay. Like here, you are varying N alpha, obviously N alpha cannot be constant. What's the time, by the way? Huh? 10:40. So you do. So now you go to something else. Done? Okay. Now I will start another one. Time dependent DFT. Now what do we require? In fact, any chemical process is a dynamical process. Or suppose if you place, say, you think about a chemical reaction, so two reactants are colliding. So that collision process, if you want to study properly, you have to go for the time dependent framework. Only difference here is the external potential is now time dependent. That means your external potential VRT is time dependent. Okay. So actually you remember Hohenberg-Kohn theorem, the two theorems were proven by Hohenberg and Kohn in 1964. So many people tried in many different ways to extend it to, say, the time dependent situation or dynamical situation. But they are all like ad hoc. You have Poincart's formalism, you have even Bloch's principle, where in terms of plane waves you wanted to expand, or some people wanted the wave packet propagation like Erich Heller's. But the thing is, they were not exact, like there is no proof, analytical proof, as you had in case of time independent case by Hohenberg and Kohn. Exactly after 20 years, 1984, in fact, Range and Gross, that's called Range-Gross proof of TDDFT. So what Range and Gross had shown that in Hohenberg-Kohn theorem, you could see that any property is a functional of density. Okay. Now Range and Gross had shown, this is your Hohenberg-Kohn. Range and Gross had shown that now the density is also space-time dependent because it is changing. In addition, you have to bring another quantity because you are flowing, you have to have a current density. So current density JRT is basically, this is current density, and this is same as rho RT into, it is not that external potential I am telling, so I will write it with some V tilde. This is what is called velocity. So actually, now you have to bring in velocity in the sense, you think about, let's say, the electron density like this. So when there is change in electron density, that means rho of r is changing. So you get, let's say, a form like this when you interact the system with or some electronic excitation, the electron density is getting shifted. But now what is happening, you have a time dependent potential which is forcing the electron density to go. That may be your chemical reaction going from one reactant to the other, okay, or electronic excitation or something like this, as if the electron density is flowing like a fluid. So, what is the current density or what is the velocity of that flow? It is this velocity. So, you have to bring in the dependence on the current, how quickly the electron density is changing. So, at a given point, what is the density at a given time? So, previously we were satisfied with only that what is the density, probability density, let us say at a given point, okay, or in some small volume element as between r and r plus dr. But now it is not only r and r plus dr, at what time you are telling, because that is changing now. Okay. So, you have to treat everything, and there is another way of looking into it, I will tell you that, that is called quantum fluid dynamics. Okay. So, quantum fluid dynamics, the equations which will govern everything over here, a dynamical process, the equations are exactly like the fluid dynamical equation of motion. Whenever there is a fluid flow in classical fluid dynamics, whatever we have learned, here the equations will turn out to be exactly similar type. We will tell where there is a difference, and those equations, they resemble with the fluid dynamical equation. So, here you do not have a real fluid, your fluid is the probability. So, a probability fluid is moving in course of time. Okay. That means the density is changing, and which is governing that? Current density, and current density is the velocity at which the typical electron density is moving, okay, the corresponding probability density. So, this is called equation of continuity. It is exactly like classical fluid equation. Del rho del T, how the density is changing at a given time at a given space, it must be compensated by divergence, this is called divergence operator of the current density. Why? It is like this, say suppose the electron density is moving very fast and the remaining part cannot follow, then there would be a vacuum and unphysical situation will come. So, that should not come, like in case of real fluid also, the fluid when it is flowing, how much is going out, that much must come in the same rate, so that it becomes a continuous flow. Okay. So, this is the reason we call it equation of continuity. Okay. Then you have one Euler type equation of motion. Equation of motion is d velocity what is this? How the velocity should change. So, I know how, and if I know how the velocity should change, I know the density, I know how the current density will change. Okay. If I know only how the density changes, that will not solve the problem. I have to know how the current density will change. So that what will happen if I solve this starting from certain initial density and current density at t equal to 0, after certain time what would be density and current density, I plug in any given property, because all properties are now functionals of density and current density. So, I will get all properties as, let us say, space time dependent functionals, electron density, current density by say functional joint functionals. So, then I can tell how that property of a system during the dynamical process it is changing. Okay. So, we can solve this equation, coupled equations now, and then I can tell you at t equal to 0, if I give some rho and some velocity, after some time what would be the velocity and what would be the density. So, I put it again, I calculate the current density, I put it in the form, the functional form of the property as a functional of density and current density, I will get a number again. So, I tell that this property after this much of time will become this much. Okay. So, that way I can follow the whole process, whatever property I require, including my reactivity descriptors. Okay. So, in this case, one important thing I must show you, this V is the V which is appearing in your Hamiltonian, that is basically classical Coulomb potential. And this one, it is coming because of the kinetic energy associated with the electronic field. So, this is the potential energy coming due to the kinetic energy, and this is what we call VQ is minus half del square rho to the power half by rho to the power half. And this is called quantum potential. You give the search quantum potential so that I can tell you something else. Quantum potential, I will give you some assignment. Did you get quantum potential? What is it is written?
The term quantum potential refers to a concept central to the de Broglie-Bohm theory, also known as Bohmian mechanics.
No, but what is that? What is the definition?
It represents a
Huh? Yeah, R is rho to the power half. Okay, and I am writing in atomic unit. Okay, so minus h cross square by 2m. In fact, why I am asking you to check this is the type what you have already learned. What is this? Minus h cross square by 2m del square. Where did you see this before? This is kinetic energy operator. Okay. So, it is coming from the kinetic energy operator, and this one is rho to the power half. Okay. If I write psi star psi as rho to the power half is basically psi. Okay. So, do you understand? So, it comes from, that is why I am telling minus h cross square by 2m I have taken in atomic unit. So, h cross is 1, m is 1, and so this is a kind of potential arising out of kinetic energy. Okay. So, here you can see, now I will go back to another thing. M dv dt. dv dt is what? Acceleration. Mass into acceleration is what? force. Negative gradient of potential is force. Here only thing is the classical potential is augmented by quantum potential, that is it. So, you can see Euler equation is just another way of writing Newton's equation of motion. So, do you understand? So, this is the way you can analyze. Do you understand this now? This mass into acceleration is force and negative gradient of potential is the force. So, here potential energy is the classical augmented by a quantum potential arising out of the kinetic energy of the electrons. Okay. Now, then if you go to the orbital picture, this density, like if I write as psi I mod square as in cone sum orbitals. So, you remember in case of cone sum scheme, in cone sum scheme we had minus half del I square plus V effective I psi I is EI psi I. Remember this was psi I for all I. This was your cone sum scheme. Okay. And V effective, you remember, it contains external potential, Hartree potential and exchange correlation potential. That is your V effective. Okay, one body non-interacting potential. In case of time dependent situation, so previously this V effective was a function of R. Now it is a function of R and T. Here psi I was function of only R, here it is a function of R and T. This Ri, T. Okay. This one is now so you can see it's just the way you go from time independent Schrodinger equation to time dependent Schrodinger equation, or time independent Hartree-Fock equation to time dependent Hartree-Fock, also written in this same fashion. But here only orbital will do the time evolution and see how the cone sum orbitals are changing, because now my effective potential contains the time dependent part, and that is why the wave function will change. Okay. But only one difference, this computational difference that I am telling, that is there everywhere. This one, you remember, this is following a variational principle at every stage, so that I can do the iterative techniques. Here, this is a time evolving situation. It is not variational the way we have learned the variational thing. Here at t equal to 0, I will start with some psi I, say some psi I at r at t equal to 0, construct the density and do effective potential, etc., then solve it. First I will have to do this. At t equal to 0, I get the iterative solution, final SCF solution. At t equal to 0, I plug it in. Then I do not have any handle. It is a time dependent problem. What will be there at the next time step? I cannot do an iterative scheme. So, that would be going to the next time step. Again, 2 delta t, 2 delta t, 3 delta t, and that way you get the psi and the density at all different time steps. So, when you do the computation, if you really want to write the computer programs, you have to remember, in one case you are doing iterative solution, but here you do iterative solutions at t equal to 0, get the SCF orbitals, the corresponding density, plug it in the time dependent framework at t equal to 0, then at delta t, 2 delta t, etc., the time dependent problem you cannot touch anymore. Okay? So, I stop over here and then we'll see, we'll talk something else. Actually, there is a zoo of functionals. You have many functionals. Some representative I am telling. So, first thing, if I write, let us say j of y as a to b f x y y prime y double prime dx. Let us say this is a general one. If your functional is only up to y, remember Thomas Fermi, only rho to the power 5 by 3, Dirac exchange, only rho to the power 4 by 3. So, if I take a Thomas Fermi Dirac theory, that functional would be local density approximation. Okay, this is basically homogeneous electron gas, only density, no ups and downs, gradients are not permitted. If I add the Weizsäcker, you remember it contains a gradient. So, TFDW, B-Lip, Becquet and Li-Yang Park correlation and Becquet exchange. There you have the gradient of density. This is generalized gradient type approximation. So, this is the first one given by Becquet, and then correlation he had added Lip correlation, Lip functional. It contains gradient, means it will have rho and grad rho both. Then suppose if you have second order, this one, Laplacian of density, then we will get what is called meta GGA. Here Laplacian, and also you can take this is second derivative, the kinetic energy density. You know, that is also Laplacian of psi, psi star del square, psi star del square psi, that is your kinetic energy density. So, you can add this and or Laplacian of density. There is like BB95, there are many functionals. You have to find out which functional is under which category. Okay. As you go up, accuracy improves, but the time required, that also just increases very quickly, and particularly if you have a larger system, you may not be able to even apply many of them. Then Hartree-Fock exchange gives you proper, say, antisymmetry type behavior. That is why to get better energy and other quantities, you admixture along with, let us say, other exchange, like here in B3 leaf, you have the Becquet exchange leaf. In addition to B leaf, you add your Hartree-Fock exchange also. That we will call hybrid GGA. Then people also told, why not hybrid meta GGA? That means you have both Laplacian or kinetic energy density and Hartree-Fock. So, there are something like BB1K sort of stuff. So, you get the hierarchy, and of course, the fully non-local still we do not have any functional. People have been trying, but there is nothing. So, this way you can go to the chemical accuracy. Okay. So, these are different types of functionals, and as I told you today, you may have 5,000 different functionals, any one of these categories, and depending on your requirement, depending on your computational power, how much computational power you have, you choose any one of those functionals. And accuracy also. You may not require, say, sometimes the qualitative treatment is also fine. Then many people, even they go at the LDA level. So, that is also possible. Say you feel some extended biological system or a materials, a solid state, there even LDA gives you reasonably good qualitative results. Okay. But suppose if you want to do, you want to calculate molecular dissociation energies, they are so small quantity, if your computational error is too much, obviously the number you get will be a garbage. That will have absolutely no meaning. Okay. So you have to choose a proper functional from the Jacob's ladder. Okay. You have been doing this, isn't it? When you do the DFT, you are all doing DFT calculations, isn't it? So you are choosing a specific functional, whatever teacher is telling you, just putting it there. So you have to learn which one to take when. Okay. Now I will tell you basis sets. Generally, we use two types of orbitals. As I told you, these are your one electron basis functions, orbitals. We may expand them again in terms of other basis functions. So, the typical orbitals like hydrogenic orbitals, they are Slater type orbitals, okay, like hydrogenic orbitals. So, if I call phi STO, let us say NLM function of r theta phi, this is n, say normalization constant, r to the power n minus 1 e to the power minus zeta r by a0 y lm theta phi. So, this is your spherical harmonics, okay, and this is the zeta. You use this word zeta again and again because ordinary hydrogen atom problem, generally we used to write it as e to the power minus zeta r by a0 is the first Bohr radius, okay. And other one is Gaussian type orbital, NLM, that you generally do not get as the solution, but there are certain positive and certain negative properties of Gaussian. Minus 1 e to the power minus alpha r square y lm theta phi. So, you see there is a basic difference, here it is r. So, this is the exponentially decaying function, whereas this is a Gaussian function, okay. That means this function above 1 goes like this, exponentially decaying this way at the nucleus site. This is your ST, but Gaussian will go like this. At the nucleus site, it is continuous. This is your GT. But there is a derivative discontinuity in actual wave function, and this one is discontinuity in the slope at the nucleus site. This is called a cusp condition. It was first pointed out by the Japanese scientist Kato. Say d rho dr r tending to 0 is minus 2z rho 0. So, this is what is called a cusp condition. So, Slater orbitals, they obey cusp condition, which is a mandatory condition, but the Gaussian orbitals, they do not obey cusp condition. Now, suppose you recall, even in the Hartree-Fock theory, when we do the calculation of energy, let us say Coulomb energy, that is say you have like phi I star, phi j star, 1 by r 1 2, phi k, phi l, d tau I, tau j, tau k, tau l. That means it is a 4 center integrals you have to calculate, and it's very, very, very time consuming to calculate the 4 center integrals. But for Gaussian, it would be reduced to a 2 center integral. Why? Because the product of two Gaussians is also a Gaussian at the middle of the two Gaussians. Okay. That means your 4 center integral would get converted to a 2 center integral. Okay. So, actually what you do when you go for the molecular wave function calculation, your LCAO-MO, let us say, linear combination of atomic orbitals to construct the molecular orbitals. So, your psi MO, let us say I is sum over J C I J phi STO N L M J R theta phi. Okay. So, what I am doing? I am just taking the linear combination of these orbitals. These are actual orbitals. But after that, when I go for the calculation of, let us say, if I want to even solve, let us say, Hartree-Fock equation in the Fock operator also, I have to calculate those integrals. And for the calculation of the Coulomb energy or other energy values, I have to have 4 center integrals. Okay. But you know, the product of two STOs is not a single STO, which is there in case of, but STOs, they obey Kato's-Kauf condition. GTOs they don't. But GTOs you have computational economy, but they are, so these are called primitive STOs and primitive Gaussians. Okay. So, Boyce came with very innovative idea, and that is why there is drastic change, that you write any STO, say J as sum over K C J K psi K GTO. So, what he has shown, that you expand your molecular orbital as linear combination of STOs, then for each STO you expand it in terms of GTOs. So, when you do the calculation, the number of basis functions increasing, but at the end, as you are going from 4 center integral to 2 center integral, you are gaining in computation, particularly for large systems. Okay. So, expanding STOs in terms of primitive Gaussians and then putting those STOs back in your molecular orbital expansion, that is the criterion given by this. And what he had shown, that if you add several Gaussians, it will bring back at least some amount of Cusp condition. Okay. So, you can solve two problems, Cusp as well as this one. So, following this, several computational chemists say, first of all, I should tell the name of Pople, is a Nobel laureate, and he actually developed the Gaussian, whole Gaussian series. And why it is called Gaussian, that is clear to you now, because everything now is done in terms of Gaussian functions. So, this is called Pople basis set. So he first started with this STO3G basis set. Okay. STO3G means flat. Wherever any Slater orbital you are putting, you expand it in terms of 3 Gaussians, 3 primitive Gaussians. That's your STO3G basis. Okay. Then he had shown that one thing is that when the, as I told you, when the chemical reaction takes place, it is basically the frontier orbitals or the valence orbitals. So that's why you call core and valence. Core orbitals hardly get perturbed, but the valence orbitals, again, out of valence orbitals, all orbitals are not of that importance. So he considered that now you take it this way, that will not give equal weightage to all the orbitals. Okay. So he then started what is called split valence basis set. So 631G. This hyphen means split. So each core orbital is written in terms of 6 Gaussians. Okay. Whole of core, I am just dumping only 6 Gaussians, whatever is there in the core. Then valence, I am writing one orbital as a linear combination of 3 Gaussians and another linear combination of 1 Gaussian. That means 1 Gaussian. So this is your 631G. This is called double zeta. So two different zeta. So this we call double zeta split valence basis set. Okay. You will hear these terms, double zeta. On the other hand, if I write 6311G, I will call this as a triple zeta double split valence triple zeta basis set, where core is 6, 3 different types of valence orbitals, one with 3 Gaussians and 2 with 1 each Gaussians. But then he had shown that suppose if I talk about orbitals of water, water has a bent configuration. H orbitals are spherically symmetric, oxygen has S orbitals are spherically symmetric, hydrogen orbitals, oxygen has 1s, 2s and 2p. So 1s, 2s they are spherically symmetric and 2p they are linear, 2px, 2p all. That means water would be a linear molecule if you only stick to those functions. Now those functions, let me tell you, I will go back, they are called minimal basis set. So like C2H2, I will call 2s 1p 1s. 2s 1p 1s means for carbon, each carbon I have 2 types of s orbital, 1s, 2s and 2p. Okay. And for each hydrogen I have 1s orbital. That's 2p means 2px, 2py, 2pz. Here remember, when I write the STOs or GTOs, I put NLM. Okay. So, here 1, 2 etc. they will tell me n. If it is s orbital, L equal to 0, m equal to 0. Px, Py, Pz, I will first construct P1, P0, P minus 1 with L equal to 1, ML equal to 1, 0 and minus 1, and then I will take their linear combination to construct Px and Py orbital. Perfect. So, that means for each carbon you have 1, 2, 3, 4, 5. So, altogether 10 for carbon and 2 for hydrogen. That means its minimal basis set will span by 12 basis functions. Now, 12 basis function means 12 STOs. Now, depending on how we do it, so in this case your minimal basis is this, but the minimal basis is not adequate. That is what they realized, that as I told you, that if I go for, let us say, water molecule is angular, but p orbitals are linear, s is spherically symmetric. So, you can never get the angular water. So, what you have to do in order to bring in angularity, you add some functions with the orbital angular momentum greater than your minimal basis set angular momentum, and these functions are called polarization functions. So, it will polarize the electron density so that it can give you the bent geometry. They are called polarization functions. So, what is polarization function? What are the L values in your minimal basis? You add another function in addition to your minimal basis function, which has L value. Like if you have the P is your maximum L, you add a d orbital. For hydrogen, you add a p orbital. Okay. For oxygen, you add a d orbital. These are polarization functions, and there I will get, let us say, 6, 3, 1 G star or 6, 3, 1, 1 G star. If G star means only non-hydrogenic atoms, if I add polarization. If I add polarization to hydrogens also, then I put another star. Okay. That means non-hydrogen, if I have non-hydrogen and hydrogen, then I put double star. Okay. Sometimes we will write it like G within bracket D or G within bracket D comma P. Okay, you will see GD, GDP. So, you have to learn that what exactly are you doing. Now, this is not sufficient. Suppose you are talking about systems like anions. We are talking about lone pairs. We are talking about hydrogen bonded systems. Meaning what? Now, electron density is not only centered around those atoms, it is expanded because of the anion, the extra or the lone pair. So, you have to bring something so that your electron density, like exponentially decaying, it is not decay within the molecule itself, it goes further off because of the electron density is diffused over. So, you have to add certain functions with very small zeta values, so that very slow fall in the exponential will come. So, functions with very small zeta values are added in addition to all these, they are called diffuse functions. So, you can say these are your polarization functions. So, polarization functions are adding something with angular momentum greater than your minimal basis set. Diffuse function means you add another function where with a very small zeta value, so that electron density goes to much larger distance. Okay. So, there I will write it with a plus sign 6, 3, 1, plus G star, let's say this plus is for the diffuse function, and similarly 6311 plus G star, G double star, etc. They are diffuse functions, and star is for the polarization function. Okay. So depending on your system, you would choose the proper basis set, proper functional. But there are other basis sets also. That's called Dunning basis set. This is called correlation consistent basis set. Correlation consistent means if you add them, some amount of correlation energy will be added automatically. So suppose if you have CC, PV, DZ, this is your Dunning basis. Correlation consistent polarization valence double zeta, or CC, PV, TZ. Correlation consistent polarization valence triple zeta. You will hear this in the basis set, isn't it? Sometimes they give better result because the correlation effect. And sometimes you will see OG, CC, PV, DZ, or this means your CCPV DZ basis set is augmented with diffuse functions. If they are augmented with diffuse functions, you write OG CCPV DZ, OG CCPV TZ. Okay. You will see these are standard basis sets you will get. Suppose if you are doing, you don't want to bring too much of spin orbit interaction or scalar relativistic like in Zora you do, but you are handling large elements like you have lanthanides, actinides. In the basis set, through basis set if you want to include something, you have some basis set like so this is LAN L2 double zeta or LAN L2 triple zeta. Do you know what is this LAN? Los Alamos National Lab. Okay. Actually, I had been to that place. This is the place where the Manhattan problem, say the two bombs which were there in Hiroshima and Nagasaki, they were built in this Los Alamos National Lab. So they developed, as you can see, they were talking about uranium, heavy elements. So for their calculation, they needed, and that is basically Los Alamos National Lab is like our Bhabha Atomic Research Center. This is the Atomic Energy Commission. So they developed this basis set, what you have been using without understanding what was the basic necessity of doing this. Because of the atom bombs, your LAN L2 DZ functionals, these basis sets were developed. Okay. So I think I have told you in a nutshell the functionals and the basis sets. Okay. So if you have any question, you can ask me.